Next speaker is Zollweg from Brockport, State University of New York. For those that aren't in the East Coast.
Turn this way. Oh, you're fine. What's the power? Yeah. If you'll forgive me for. No, not going to. Too many things. If you'll forgive me for using notes, as a professor, my norm is a 50-minute teaching type of thing, not a 15-minute efficient presentation thing. So first, I'd like to thank you for coming. My topic is about using soil thermal inertia to get a better measurements of soil moisture, both in the temporal and the spatial scale. And I'm going to use I will be using remotely sensed data to accomplish that. So several goals in the presentation, kind of philosophical goals. I'm setting out to develop in the next few years, hopefully a 30 meter daily soil moisture estimates, and using remote sensing data, as I said, and applying machine learning and environmental covariates to help to put this whole mass of data together. I'm also very interested in discussing any of this with any of you, and finding collaborators and partners and people who share this type of interest, machine learning, remote sensing, and how we can take the exploding amount of data that we have and make some sense of it and make some use of it. And I think perhaps I'm hoping that some of the things that I show might strike just a tiny bit of interest. You say, that looks like something useful. I'm not sure if I had time or if you explained it very well, but that sounded interesting. And I'd please invite you to share that. So the theme of today is of this meeting is applications, or a direction. And there are a lot of applications. Wildfire risk is one. Wildfire risk is fairly closely related to soil moisture and the consequences of perhaps low soil moisture. And I've always thought that using Southern California is in a red flag warning right now. It's a little too broad to really be useful. So again, the detail is important there. Flash flooding and non-point source pollution are issues that are maybe a little more relevant to where I come from in the humid Northeast. And it shows that knowing a lot about soil moisture is also very important for too much soil moisture. And those are especially applicable at the very, or needed at very tight resolutions. So thermal inertia is just the principle that wetter soils change their temperature in a diurnal cycle slower than drier soils do, because of the very high thermal capacity of water. So water helps us by being slow to change its temperature. And this is just a very generic AI-generated graph of three different soils: hypothetical, wetter, medium, and drier. And each of them have show differences in how temperature changes diurnally. So there's differences both in the relative heights, the range of changes, and in the lag times. And I'd like to acknowledge here, of course, that nothing could succeed without the enormous collection of real data that can feed theoretical and machine learning models. And without that, it'd be impossible to do anything. And here's just a snapshot example that shows real data that is the same parameters as the previous slide. And this slide here just illustrates on that different soils or at different moisture levels respond differently to to respond differently diurnally, both in the range, how much warmer it gets and cooler it gets, and the lag time. So there's information there. There's really something to know there. The environment I work in, something else. Yes, I wanted to go back and mention that because there are, and I don't even know the number, but it's lots, because there is a huge amount of data that's available, really good data in the field with incredible numbers of features collected and timescales, that it is possible to make some extremely reliable models of how soil temperature changes and responds to over time based depending on soil moisture. So we can really build some strong models in the soil inertia side. There is a problem though. To really use soil and moisture or thermal inertia effectively, one needs to have data that's at a very high temporal resolution, as well as a high spatial resolution, because I want to get 30-meter cell size soil moisture eventually. And you also need to have very high temporal resolution, like hourly. And that's a big ask, I think. So how do I suggest addressing that problem? Well, there is a resource called the GOES satellites set in space. They're in a geosynchronous orbit. There's several of them that work together. They're in geosynchronous orbits, and they take a snapshot of the temperature of the Earth, the temperature of the top of the clouds, and a whole bunch of other things every 15 minutes. Sometimes it's an hour. I'm not sure exactly why, but they take these measurements very, very frequently. It's just sitting up there above Canada somewhere, taking a snapshot of North America. And it takes the snapshot very, very, very quickly. The problem is, however, that every cell is 2 kilometers in size, which isn't bad for something in space, but it doesn't really address my 30-meter goal. So what's the strategy that I'm using? And that is to use something called downscaling. So by using measurable parameters that are at a much finer scale on the Earth, and using those differences to see what the differences in temperature. We can measure temperature nicely at 30-meter resolutions using the Landsat satellites, which don't come around very often. It's this whole question of always temporal and spatial resolution trade-offs. So we do have Landsat data, but it's very, very rare to get really good Landsat data for the surface temperatures. So what I've done is take the GOES and you compare it with the handful of good Landsat data, and then you use parameters on the ground, such as anything that influences surface energy balances, radiative properties, etc. And some of those data sets would be, for instance, relative terrain position, which is whether you're in a depression or a mound, NDVI, albedo, SAR. And I can't wait. When is it going to launch, Mike? I don't know exactly. The INSAR coming up, and also the temperature, elevation, aspect, and slope. All of these parameters are either static and well-defined, or are not static, and that makes them useful, but also available at a decent resolution. These can be used as covariates in some sort of a machine learning model. And I've chosen a support vector regression. And support vector modeling it's absolutely fascinating, but it's a machine learning model that has a number of advantages, such as it handles data sets that are very, very large, have many variables, maybe noisy, nonlinear. The variables might not actually be very independent, which is a no-no in many other statistical methods. So it's a very effective method, and using it, I've been able to downscale these GOES satellite data at 2 km down to 30 meters with a fairly good amount of success. So it actually allows me then to get a 15-minute surface temperature from GOES satellites. And again, we have levels of abstraction, I realize, but we're tightening those levels of abstraction down. Additionally, a machine learning model has a very important advantage, and that is that you can interrogate it. There's a tool called Shapley additive explanations. It's game theoretic based, and it is a way to assess the importance of every single parameter on every single result in your model and really understand what it's doing. And this Shapley analysis that you can do once the modeling is done allows one to interrogate the model, to learn from what's happened. So there's a scientific basis, and also it gives you a little more confidence when you see how it's actually doing it, and that it's not a black box. The model, this whole strategy that I've developed is data agnostic, which is why INSAR might remind me of it, but I can substitute out measurements from INSARs because it has an L band, et cetera. So I think this is data agnostic. You can pull out one data set and put in another one that might improve the results. Again, that's similar to modular architecture and scalability. And I do want to thank you, and I have lots and lots more to do, and I'm very excited about doing this in different places and different times and for different applications. And I'm only beginning to grapple with the amount of data that it's going to take to really do this. And I'm not sure what the next level is above terabyte, but that's in sight. And as well as buying AWS virtual supercomputers and stuff like that. So, but I'm very interested in this, and hopefully I can find some others too. Thank you.
I would say that when I saw launch day, so they said it was June 18th. I got $20 that says that's not the date they want. It's never the date to say. They're 30th date. They got out there.
So they're gonna launch soon, right?
Yeah, oh yeah, holy sooner.
It's always just a few months away.
I'll mention, so you have the GOES satellite, and in the future, we're hoping that it converts to a constellation of GeoXO, is the latest geostationary orbiting, geostationary satellites across the US, which would be 3, east, center, and west.
Yes.
We'll see how.
That would be an improvement. GOES is getting a little long in the tooth in certain ways. Yeah, and again, that reinforces that there really is an explosion in data and computing power to go with it. And these approaches, I think, are quite doable. So.
No question about this. We don't allow.
Today, Dr. Juhu again. I've known this, University of Maryland.